So taking a look at a sapling question, it says, draw the conjugate acid for the following base. Remember to include charges and non-bonding electrons where necessary. All right, so for this one, what you'll see here is, okay, so they're telling you, what do the instructions tell you? They're telling you this is a base. What do bases do? Bases are electron rich, right? And they're assuming here is acting like a Bronsted base, meaning it's a base that's gonna get a hydrogen. So if this was a base, what does this conjugate acid look like? Well, basically what they're saying is in your mind, if this reacts with H+, what's the reaction gonna be? What's the product gonna be? So we're saying, essentially what they're saying is, they're not showing the H+ now. They're saying is, what's the conjugate acid of this base? All that's saying is, here's the base, find the most electron-rich part of the base, that'd be the nitrogen lone pair, and that is gonna react with an H. And what would that product look like? Well, that product would look like, right, the lone pair would go and grab the hydrogen for our mechanism, equilibrium arrow, and the conjugate acid then would be the nitrogen bonded to another hydrogen. That's its conjugate acid. Another interesting way to add a layer to this, which side would the equilibrium lie? Here, towards the starting material, well, I have the left or to the right? Which way would the equilibrium lie? Left or right? What's more stable? What's less reactive? Things on the left or things on the right? Things on the right, right? This would be no charge. So the equilibrium is actually going to lie this way too. But this is a base, there's this conjugate acid. So a conjugate base, or base, to get its conjugate acid, you have to have it react with a hydrogen. So here's another conjugate acid, conjugate base question. So here they're saying, draw the conjugate base for the following acid. Remember to include charges and non-bonding electrons. So then now they're saying this is an acid. What would this acid look like if it reacted with a base? Right? Here's an acid, react with a base, what does that product look like? So I'm going to redraw it a little bit. This is what it was like before. I'm just going to redraw it a little bit. I'm just going to draw it that way so you can actually see the OH bond. If this reacts with a base, so we put OH minus. Electrons go there. So we break that OH bond, right? Because you're told this is an acid, and we want to find this molecule's conjugate base. So it would be this molecule without its bond to hydrogen. Equilibrium arrows. This, of course, indicates that this carbon is bonded to this oxygen twice, and then to two CH3s. So we can draw it a different way. Right, so this is the conjugate base of this starting material. This base has a conjugate acid, which is this right here. So whatever's on one side of the arrow, if you're the acid on one side of the equilibrium arrow, on the other side of the equilibrium arrow, you are a base. This is the base on the left. On the right, the species that after it's reacted is an acid. And again, the equilibrium would lie towards the right because there's no charges here. More stable. All right. I have another acid-based question. It says nitromethane is an organic compound with the molecular formula CH3NO2. Draw a complete Lewis dot structure that shows all bonds, unshared electron pairs, and minimize formal charges where appropriate. So this is hard because you actually got to know what this looks like as a Lewis dot structure. That's what makes this tough. So you want to put nitrogen in the middle. You know it's bonded to both the oxygens. You also know it's bonded to a CH3. And you know overall there's no charge here. But if you leave it the way it is right now, both of these oxygens would have minus charges, and that would be 2 minus, so that can't be right. So you actually have to go here. You start filling in electrons. You'll see everybody has a full octet, which of course is the most important thing. So this is actually the Lewis structure of nitromethane. This is actually the Lewis structure of nitromethane. So this makes this difficult at first. I'm also going to just draw this a little different. I'll put a 2 there and show this CH bond, because what they say then the next part. So they made us draw it out, so there it is. Then they say draw a complete Lewis structure for the conjugate acid of nitromethane that shows all bonds, unshared electron pairs, and minimized formal charges. Okay, so actually I didn't need to draw this one out. I could have drawn out, if they asked me for the conjugate base of this, right, the conjugate base of this, where this is the most acidic is actually on this CH bond is really reactive, because if I put a minus charge here, what can that minus charge do? What can that lone pair do that's going to make it stable, make it more acidic? So if I break this bond right here and draw the conjugate base of this, would be a negative charge there. So let's see, let me just draw that out. It's still there, okay. Why is that stable? If I do this reaction, why does that happen? What's the hybridization state of that carbon? What's it next to? There's a pi bond. It's going to be sp2 hybridized, and it can do resonance. So that's going to make this stable. So that's going to make this actually a pretty good acid. That's not what this question's asking, but that's another little added fun. So what if we actually answer the question? So that's this acting as an acid, and that's its conjugate base. And it could happen because this has resonance stabilization. Another thing we could do, though, it says, what would this molecule's, right here, conjugate acid look like? So where is this molecule most electron rich? Where is this most likely to react with an H+? On the O-. So the conjugate acid would be that. That's what its conjugate acid would be. I think the hard part here to remember is, so here's a molecule. Can it be an acid? Yes. This bond is reactive because we form a stable base. Can it be a base? Yes. It has an O- with electron density, and we can form a stable product, right? So things like water, right? Water is a classic example. Water can be both an acid and a base, right? This is obviously a little more complicated, but same idea, right? Things can be acids and bases. All right, got an ugly looking chair here drawn, but it'll work. It says, given cyclohexane in chair conformation, substitute 2 of the H labels with a methyl and a tert-butyl to construct a more stable conformation of trans, meaning opposite sides of the ring, 1 tert-butyl, 3 methyl. Okay, so first thing I would do is draw it with wedges and hatches. Tert-butyl is on the carbon 1, and the methyl is on 3, and they're opposite each other. So 1, 2, 3, 4, 5, 6. That's what trans 1 tert-butyl 3 methyl cyclohexane is. Now we need to put it into a chair conformation. So the first thing you need to remember is tert-butyl is a big group. And so if it's a large group, you want to make sure it's which place, axial or equatorial? Equatorial. And I like to think of it as up, so I'm just going to find an equatorial position on the ring. It doesn't matter where at this point. It could be anywhere. And I like to think of the wedge as up. And I'm going to pick this one as my tert butyl. So I'm going to arbitrarily make that carbon 1 there, that footrest carbon 1. That's where my tert butyl is at. So the methyl group needs to be on carbon 3. I could number this way, 2, 3, 4, 5, 6, or I could number this way, 2, 3, 4. It doesn't matter. I'm gonna go this way. So this is carbon 2, this is carbon 3. So the methyl group is on carbon 3, and if the tert butyl in this case is pointed up in equatorial, the methyl group has to be pointed down. So on carbon 3, what position is down, axial or equatorial? Axial. So that's where the methyl group is at. The methyl, Me, is at its axial. And this would be the lowest energy conformation because the most important thing is to get the big group, tert butyl, equatorial in a way. Now you could do this a bunch of different ways, right? You could do this a lot of different ways. As long as the two substituents, the tert butyl and the methyl, are 1, 2, 3 carbons away, and one's pointed up and one's pointed down. Does the tert butyl have to be pointed up? No. The tert butyl could be pointed down, but as long as the methyl then has to be pointed up. They have to be opposite. They have to be trans. So it's just one of many, many possibilities. So looking at this question, it said, for the following reaction, indicate which reactant is the Lewis acid and which is a Lewis base. So the first thing you need to remember is what's a Lewis acid and what's a Lewis base, and whose category they fall under. So a Lewis base falls under the category of electrophile or nucleophile. Lewis base, nucleophile, electron rich. Okay, so you look at these things and you say, well, I don't know. This is a plus charge, so that doesn't seem like a nucleophile or a Lewis base. But I'm not sure. I've never seen a benzene ring, or this arene ring, be a Lewis base. I'm not sure about it. I'm going to wait. I don't know what that is. They also want me to identify the Lewis acid. What's an acid? Acids are electrophiles or nucleophiles? Electrophiles. They're electron rich or electron deficient. Well, this guy's a plus charge, so that must be the Lewis acid. Well, if that's the case, then this must be then the Lewis base. Otherwise, the reaction won't take place, right? Two Lewis acids don't react. So you can remember any of these reactions. If you can identify one thing as the nucleophile, the other thing must be the electrophile. If you can identify the electrophile, the other thing must be the nucleophile. Now, the cooler part here to remember, so obviously this is electron deficient because it doesn't have a full octet. Right? So it doesn't have a full octet, so it's electron deficient. That makes sense. Electrophile, Lewis acid, it's going to accept electrons. Now this is a Lewis base because the mechanism here, if I just said what new bond was formed, if I number my carbons, as you always should, 1 and 2, it looks like to me carbon 1 all of a sudden is bonded to this bromine. How did that happen? 2 electrons in every bond. Where do those 2 electrons come from? Well, they came from this pi bond, which attacked the bromine, which left carbon 2 with a plus charge because it lost electrons. All right, so Lewis base, Lewis acid, nucleophile, the pi bond's the nucleophile, the electrophile is bromine, Lewis base, Lewis acid, nucleophile, electrophile. One step nucleophilic attack, one of the mechanisms we learned. So let's draw a Newmann projection of this. So I always like to number the carbons 1 and 2 that we're kind of looking down. Now the other thing where we always get, as in an English speaking country, we always like to look from left to right. But you also could look from right to left. And they'd be different Newmann projections, right? Same molecule, but different Newmann projections because the front carbons in right to left is 2, the front carbon in left to right is 1. So let's draw both. So if we look at this, if my eye was looking down here at my head, I would see an H. Nothing on my feet, but there's an H in my head. So something to my right, something to my left. There's an H in my head, and my right hand was then OH. And my left was a ethyl. So there's a CH2, CH3, CH2, CH3, there it is. As I look down to carbon 2, what do I have at carbon 2? Something at my head or my feet? I have something at my head. So there's the CH3. To my left, I have an OH, and to my right was an H. And that's what this is, carbon 1, and then behind it was carbon 2. Now if I did the other way, looking from right to left, again I have something in my head, and something on my left and my right. We can see that, so hopefully everybody sees this as eclipsed. So in this case, at the top would be a CH3. To my right would be the OH, which is not going away. The H there. Walk to carbon 1, there's an H that's up. To my right is now that ethyl, 2 carbon piece. And to my left is that OH. This is carbon 1, and then behind, or no, this is carbon 2, and now behind it was carbon 1. So both of these are valid valid Newmann projections. It depends on, am I looking this way or am I looking this way? Usually I'll prompt you and say, I want you to look from 2 to 3 or 1 to 2. So it's easier to grade. But I'll usually tell you. So be ready. You can look at it this way, right to left, or left to right.